Hello people, in today's session we'll understand about the normality of data, which generally we call as a normal distribution of the data or not a normal distribution. So normality assumption of a data is really important in many of the statistical tests, because some of the tests we perform with the normal data, some of the statistical analysis we perform with the not normal data. So normality tests are used to determine if the data set is well modeled by a normal distribution and to compute how likely it is for a random variable underlying in a data set to be normally distributed or not. As I was telling, it's a prerequisite for many statistical tests, sometimes like correlation, regression, t-test, analysis of variance, or many other. If the data is normally distributed, then we go with the parametric test, and we use the non-parametric test in case data is not normally distributed. Normality can be tested by using some of the graphical method, including some of the statistical method as well, like as Kolmogorov-Smirnov test, or maybe Shapiro-Wilk test, or the most famous test which we use is the Anderson-Darling test. Graphical method include comparison, like comparing a histogram of the sample data to be normal probability curve and the normal probability plots, or sometime which are also known as the QQ plot, which is the quantile-quantile plot. So quantile-quantile plot, if the data were perfectly normally distributed, all the points would fall in one line. If the data deviates from the line, then the less normally distributed the data is. It is important to note the normality tests are not always necessary, and the non-parametric test can be used if the data are not normally distributed. So let us understand what is the normal distribution of the data. We expect our process data, whatever we have collected, to show the bell curve. And when you look for the bell curve data, what do you mean by bell curve data? Bell curve data is your mean in the bell curve data is equal to median is equal to mode. These are the main feature of a normally distributed data, which means if I draw a curve of the data, and it's a start from here, goes here, and goes here. So in this case, you will see the highest point of the data is this. That means mode, most frequently data, which is perfectly in the center as well. So the same is in the mean. And this is both the side. If you arrange in the descending order or ascending order, the same point will come. So it's a median as well. And this is what we call as an bell curve. Look like a bell. Mathematically, if you look for this bell curve, in this case, we'll see that how much of the data will fit within the given standard deviation. Suppose you look for the mean value, and here is your standard deviation, assuming on an average, your average is 90 and your standard deviation is 1.5. So as per this, what is the mean plus or minus 1 standard deviation, or mean plus or minus 1 standard deviation? So let's say if I see mean plus 1 ST, this is your upper range. And here, if I say mean minus 1 ST, that will be your lower range of the data. In between, if I say mean plus or minus 1 standard deviation, then approximately how much is the percent data should fall within this given range will be 68.28% of the data should fall. So if in actual process you are looking for average is 90 and standard deviation is 1.5 as a mean plus or minus 1 standard deviation, so then how much data you are expecting? The lower range, let me do here. This is your mean plus or minus 1 ST. And this side I will say the lower range, and this side I will say the upper range. That will look better. So in mean plus minus 1 ST, what will be your lower range as per this data? Lower side will be you have the average value minus 1 time of standard deviation, which will become 88.5. And in the upper side, you will have average value plus 1 time of standard deviation, which is this value. And here we go 91.5. So as per this data, mean and standard deviation, your lower side is 88.5 and upper side is 91.5. Between these two values, 68.28% of the data should fall. Then we call it a normally distributed data. If I look for the mean plus or minus 2 standard deviation, then suppose the same average and standard deviation I am taking. So 2 time of standard deviation, you will be multiplying this 1.5 into 2. So lower side will be 90 minus 3, which is 87. And upper side will be 90 plus 3, which is 93. In this condition, around 95.45% of data should fall between the 87 and 93. Or if you go further and you look for mean plus or minus 3 standard deviation, mean is 90, standard deviation is 1.5, then lower side will be 3 time of standard deviation from the mean and upper side will be 3 time of standard deviation from the mean. So lower range will be 85.5, upper range will be 94.5. In between these two values, your 99.73% of data should fall. And this is also called as an empirical rule. This is also called as an empirical rule. Now, if we look from the statistics point of view, when we perform for normality test, Anderson-Darling test, this is basically the probability plot or normal probability plot of your data. Anderson-Darling test will help you to identify either the data is normal or not normal. So that works on your hypothesis testing. So assuming my hypothesis, I am assuming my hypothesis is that data is normal. So my hypothesis data is normal will be proved as a null hypothesis when the p-value of Anderson-Darling test is greater than 0.05, and I will call data is normal if I run Anderson-Darling test. Opposite to that, this will be your null hypothesis and data will be normal. But in case your p-value of Anderson-Darling test comes less than or equal to 0.05, then this is an alternate hypothesis, and my hypothesis here I failed to prove the null. This means it's an alternate and data will be not normal. So hypothesis, I am planning data is normal. If p-value is greater than 0.05, it's a null hypothesis, data is normally distributed. But if the p-value is less than or equal to 0.05, then data will be not normally distributed. How do we do this? Let us understand in the Minitab. So here is the Minitab I'm just opening. I will run both the tests for the normal as well as for the not normal data and will show you in respect to the p-value. So I'm just generating some random data. This random data may be somewhere you are doing per hour transaction between on an average, let's say 15 to 20. I'm generating some value in the decimal as well, not only the count. And here on an average transaction of the team per hour, I have generated for last, suppose 17 plus 2, let's say 20 hours data, right? I wanted to check either this data is normally distributed or not. So one is the mathematical way I can do, like as calculating what are the plus minus 2, 3 standard deviation limit, and then look how many data values are falling. Or another way, as I was telling, go to the Minitab, use your data here. Now go to the stat, basic statistics, and here in the bottom you will see the normality test. Click on this, select your data. By default, Anderson-Darling test is selected. Click on OK. And now read the p-values. If I look for this data and the probability value of this data is 0.514. 0.514 p-value is much higher than 0.05 of the threshold. So as I was explaining in the Excel sheet, if your p-value is greater than 0.05, your data is normally distributed. And in this case, we'll be using the parametric test when we do the data analysis. But in case your p-value comes less than 0.05, then it's a not normally distributed data, and we use the non-parametric test. Let's do one thing. Let's generate some not normal data in Minitab itself. Maybe I'll go to the calc, random data, and select any kind of distribution. Maybe exponential I'm selecting just for case. You are selecting number of rows, maybe 50 data point you are generating, where you are storing in the column C2 with the scale of maybe, let's say, you can say as in 0.5 if that works, and the threshold is 0.01. So these values are, I have generated exponential data. Because I am generating the exponential data, obviously this will turn out to be an exponential distribution. So if I calculate the probability distribution of this data with respect to the normal, this data should come as a not normal data, which means the p-value of Anderson-Darling test will be less than 0.05. Let's see here. I select this data, click on the same Anderson-Darling test, go for OK. And if I look for the p-value here, then the p-value of this data is much lesser than 0.05. That means your data is not normally distributed. How to deal with the normal data and how to deal with the not normal data, I will be telling you in the upcoming sessions. Thank you so much, people. I'll see you in the next session.